Hi and welcome. Thank you for joining me. Today's a bit informal. I wanted to do some programming for fun. Yeah, so just wanted to find something that was like basically unrelated to anything I would do in a job or for a podcast or anything like that. So and I also wanted to, I'll chat a little bit about like just what it's like to be a software engineer. Because yesterday I was talking to a listener to the podcast, and they had just gone through like their like boot camp, and they were asking me some things about what it's like, and I was telling them stuff, and so I thought maybe other people want to know what it's like, so figure we could chat about that too. But if you have any questions or whatever, definitely anything's game, well, anything I feel like talking about. So, how did this all start? We will switch here and I'll show you. And by all, I mean, why am I doing assembly programming? So, a while back, I created this operating system called the 3L project. And I wrote my own operating system from scratch. So it runs on x86 64 systems. So that'd be like any modern AMD or Intel computer. It'll just run on bare metal, not running on Linux or Windows or anything. And I now have a Mac M2 chip, which is ARM based. And so this system won't run on it. It was specifically written for the x86 architecture. And I've wondered, like, hey, what would it take to adapt this to make it also run on an ARM 64 system? So yeah, that's what I basically wanted to explore. I have no idea what it's going to lead to, but yeah, that's the general idea. So let's see. We will first check my stream things here, and okay, that looks fine. So yeah, if you can't hear me or something, let me know. But yeah, so I figure I'll show you what I had in mind here. So the first thing that I wanted to look at is this Hello World and ARM64 assembly. And so for this, I purposefully I did not want to prepare too much ahead of time because I just thought I'd show you how I work and approach things like this. So I will say I've done ARM assembly programming, but it's been probably like 8 years or something, and even then I did barely any, and it was for 32-bit ARM. So it's like I don't know if it's really that much different for 64-bit ARM, but technically different. And I made it. I wrote like a bootloader, I think, for the Raspberry Pi, which was an old version of Raspberry Pi back then, of course. I don't know how many years ago it was. It was a while ago, right? So, yeah, it was a ton of fun, but I am not like at all especially good at ARM programming or an expert on it. So we'll just be learning together. So what I really want to do is figure out how, with the 3L project, to like there's sort of some core parts. Like you have your operating system, and most of that code I wrote in Scheme that gets compiled to C. And once it's in C, I could easily compile it for ARM64. And so that part's easy. So most of the code I should be theoretically easily able to run on 64-bit architecture. But there's some other code that has to run before that. And there's also some differences in how things run even once this code. So like I have all this code for the OS. It can be compiled to run on an ARM64 system. But different architectures treat hardware differently. So on an x86 system, maybe I can display characters on the screen by writing to a specific memory address. That address might be different on a different architecture, or maybe there's a completely different way of writing stuff to the screen, right? So while technically most of the code can be just compiled to run on ARM64, that doesn't mean it's really going to work or do anything. And so I really want to figure out, like, what is it actually going to take to make my operating system run on this ARM architecture. But that is, I'm really not an expert at this, and I like kind of don't know where to begin. Because what I did for the 3L project was I made it so that it basically uses a different operating system called Bare Metal OS to launch my OS. It was sort of a shortcut. Once it launches my OS, it's not using Bare Metal OS anymore. But I used that OS to basically take care of a bunch of bookkeeping that has to happen to set up hardware before you can start using it. So I don't know if I can do that on ARM. The Bare Metal OS that I used was specifically written only for 64-bit x86 architecture, so I can't use that. So it's kind of like going back to a really, I don't know, long ways away, like way back to the beginning, it's like when a hardware boots up, you have to do all sorts of like initialization, like, just setting it up to be in different modes, and you have to like detect what modes might be, say, available. And all sorts of that kind of stuff. And yeah, you can see in the slides here I have from the OS, I'm like writing bytes to a memory address, which is overwriting the characters on the screen. So you can kind of see how that works. But I'm guessing on ARM systems, it'll be different. So anyways, I'm sort of like, I don't know where to begin. And whenever I am in that position, I'm like, I want to do something that I know I can get rolling. I don't want to be stuck, like staring at the screen, feeling overwhelmed. So my first thought was, let me just get some ARM assembly code running. So I haven't tried this. I don't know what sort of issues I might run into. But I thought, we could try it together. I thought this thing would make it easier to zoom in so you could see it here. All right. So I think, hold on, I need to do some OBS things to, hey, all right. Apparently I didn't have that centered. Okay. So, never mind that. So yeah, what we have here is I just found this, what looks like a really basic Hello World and ARM64 assembly. And I just want to get this working. So if we scroll down here, you can see it's got some code. Can I just copy and paste this and have it run these commands? I don't know. We're going to find out. But what I can, tell right from this is, this is expected to be running on Linux, I believe. And this is important. So we're running an assembly program, but you can run an assembly program within an OS, and you can interact with that OS. And so in this case, we're calling this write function. So this is in C. We're going to write the equivalent in assembly, but in C, it's much easier to read, right? So we're calling write. Write is like a kernel system call. And so we're basically telling Linux, hey, write this data to this place. If I'm doing this in my own operating system, this function doesn't exist. Like write, it doesn't exist. So Linux and the operating system is doing some work for me when I call it this way. So I can't directly use this in my OS, but it's like one of those things I just want to, I don't know, the way I approach things, I like to get things working, and then I can slowly transform them to whatever it is I'm attempting to do. So if I can get assembly code compiling and running and I can mess with it and make it do stuff, that's like step one. And then after that, I can work on figuring out, okay, how do I do whatever this write function is doing in my own OS type of thing. So yeah, that's sort of my approach to this, and we'll see what happens. Get a drink of coffee here. I don't know. I like to drink coffee when I'm programming. I don't know if that's something other people do. Actually, I do know. Talk about like being a software engineer. That's a pretty universal thing, right? Like if you haven't been a software engineer, you go into the office, there's probably going to be coffee available, but that's probably true for any sort of knowledge-based work. Yeah, so that's nothing unusual or exciting. But yeah, I just want to get into this here and see if we can get this working. So I'm just going to copy and paste this code, and I'll like explain a little bit of it, at least the parts that I know. Oops, wrong Emacs. So I'm running a virtual machine, a Linux virtual machine on my Mac here. It's what I do all my actual programming in, because I can't stand dealing with Mac for compiling software and getting stuff to work. And I've already got all this configured from running Linux for many, many years, so it all works great. Anyways, besides the point. All right, so in assembly, if you see this like period and then some sort of name like data, or you see text here or global, these are basically like directives to the assembler program to tell it what the stuff after it is for. So like the data section is saying, hey, this is data. It's not code that I want you to run on the architecture, the CPU or whatever. And so yeah, we have a data section, and then text is how you denote that you have code that you're actually going to run. So these are like the actual instructions. And I think global start, so I think this is creating a label. And so you can create these labels, and I think you can make them whatever you want. So like we could do something like dot global foo, like that's fine too. I don't know why it's indenting everything like that, but and then later on you can actually reference foo and like jump to it. So you can send it a jump instruction and it will jump to it. And that's super useful. But anyways, that's what that is. So once we have in here, they've added comments to like show us what it is compared to the C code. And so in this case, we can see all these instructions here are for this write call, this write function call, syscall is what it is. And then we also have a syscall to exit the process. These are just both Linux syscalls. They're just something Linux created, and there's like documentation that tells you how to use them, that kind of thing. So yeah, that's what this is at a high level. We'll look into it more. But first, I want to see if we can actually run this thing. So I got my terminal emulator up in Emacs here, and we'll switch back to here, and they give us a couple commands, and they called it hello. So I need to rename my thing if I want to be consistent, which we can do. So I'll just use dired to do this, which is the file explorer within Emacs. So we'll rename this to hello.s. Bam. All right, we're good. So now if I copy paste this, this is telling the assembler program to take as input hello.s and produce as output the assembled binary hello.o, or object file, I should say. Let's see what happens. Oh, hey, it works. Apparently I have as installed. So you can see, yeah, we now have hello.o, and if we can open it up. right? Looks like that. So actually this is interesting. I can show you some things. So this is like an ELF binary. ELF is like a binary format that Linux understands. We won't go into that now, but yeah. So, and you can even see this data string from our assembly code showing up in here. So that's cool. You could open this in a like a binary editing software. In fact, I can actually do that in Emacs if I remember how. Bin hex, I forget. Anyways, so you could do like, I think I can do. Anyways, I don't remember. But anyway, not important. You could actually view the bytes, and you can compare these. Like you can look up what this would be encoded as, and it'll actually show up in that file. So it's kind of fun. You can't really do that in other things that are compiled as easily. So that is cool. Let me get a drink here. All right. And just checking on some things. All right. We got our live stream going. Cool. All right. So let's go back to here. All right. So we got our assembly code. We assembled it. What do we do next? So next, we need to link it. Is that what LD is? I believe. First, we assemble an object file and pass it to the linker. All right. If all goes well, this will generate our, what is a, so I know what a linker is, but I don't feel like I can give a great explanation. Takes one or more object files, so that's what we produced was that object file, that .o file, and combines them into a single executable file or library file or another object file. That does not really explain a whole lot. I think the the short of it is it makes it run on Linux here. I wish I could give you a better explanation, but my memory is way too rusty to remember how to explain this usefully. So anyways, we'll just see if it works. We should be able to just run it after this, and it should work. I don't know. Let's find out. So go to our terminal. All right. Hey, it didn't give us any errors. So now you can see okay. Oh. So if I can figure out how to use this terminal emulator. Anyways, not important. We can just go back here. You can see we have a hello file as well. And it actually looks very similar to the object file. But anyways, if we go back here, we can do hello world. Or is it just hello? Error in process filter, invalid face. Okay. Thanks, Emacs. I wish I knew how to use this. I don't think my terminal emulator is working very well, so we will open up one I know how to use better. So let me go to here. Oh, let me make this bigger so y'all can see it. All right. Oh. Wow, how did I get there? All right, source. All right, now we're in the right place. Okay, so, all right. Yay, look at that, it worked. Ah, that's so cool. So, hello ARM64, we did it. So now we can go back and look more at this. So let's see. what we have is back in this data section, we defined a label called message. And we are telling it that the data is ASCII. So we can pass it a string and it's hello world with a new line, or hello ARM64 with a new line. And then you'll notice down here at this line, we're passing an argument to the write syscall. So const void buff. So this is the buffer that the kernel should use to write this data. And what we're doing here is, I believe LDR would be something like load type of thing. And so what we're saying is, hey, for register X1, so a way to look at this is when we make a syscall, the syscall interface expects the arguments to a function to be in a set of registers or memory locations. And so in this case, we're saying the first argument is FD, the second argument is a pointer to our buffer, and the third argument is essentially the size count in this case. So the size of the data in bytes, I believe, that you're writing out. So our first, so we're moving number 1, standard out file no. Apparently this is just some special Linux thing, into register X0. And then second, we are moving, so you see this equals message into X1. So I believe what this is doing is loading the memory address that points to our string, our data here. So at a hardware level, to interact with memory, you do it in terms of the memory address. And each process that the kernel runs gets its own address space. And so the way it works is we run our binary. It gets loaded into memory. And this equals message, I believe it might be the linker that does this. It's going to set this when it links it to the actual location that this data will be loaded into memory. And so this is saying, hey, kernel, our X1 argument, our 0, 1, number 1 argument, our buffer pointer is this address. But in the assembler, we don't have to like you could actually, I believe, instead of doing like equals message, you could like, I don't know, write like, you know, the actual memory address here if you knew what it was gonna be, and it would work. But this just saves you a bunch of work. You don't have to manage that. And we're also doing a similar thing with length here. So you can see we create another, essentially a label here. And this is interesting. This is like sort of the way you can interact with an assembler. This period tells you like, it's like a reference to the current memory location, I believe is a way of saying that. And message is the start of, or it's the memory location here. So what we're essentially saying is take our current memory location and subtract that from the start of message. And that will give us the length of this string. That way you could come in here and add bytes to it. You don't have to recompile the length. So what you could do, instead of doing equals length, you could be like, you know, number 10 or something, if it's like 10 bytes long. I don't know if that's actually the way you do it, but it'd be something like that. So you could hard code it. But this syntax allows you to not hard code it. So that's cool. And then write is syscall number 64. So it looks like the way it works on Linux, if we want to trigger a syscall, is we load a number. This is basically just a magic number that's defined in documentation into the W8 register. And then we do this SVC. which invokes the syscall. And so the way it works is you invoke a syscall. When you do that, the architecture unloads your process from memory and loads the kernel into memory. And the kernel goes, "Whoa, look at this, I had a syscall. What do I gotta do? What do I gotta do?" You know? And so it goes and looks at what is in W8, and it's like, "Wow, number 64. That means I need to write some data." And so you're basically like, instead of like, in a higher level language, you just make the function call. That's not how it works at a hardware level. So instead we use syscalls, which is basically like putting magic numbers into a known register. And then the kernel checks that value when it gets its syscall code invoked, which happens when we do this SVC here. And this is something that is different per kernel, per operating system. So in, maybe on Windows or Mac, maybe there is no syscall for write, but there probably is, but it could be a different number. And the arguments to it could be different. This is something specific to the OS. I'm gonna take a little break here and get some fluids here so my voice doesn't dry out. All right, so yeah, that's how this whole write thing works. And then this syscall exit. So it's basically the same idea, but we want to tell Linux to like unload our program and that everything went fine. And part of the way you do that is by setting 0 into this register. 0 is a status that you pass when everything is fine. If something went wrong when your program was running, you put any other number in there. So we put 0 in there. Then we put 93, which is the magic number to say we want to exit the program. Then we invoke the syscall and our program is done running. So yeah, that's actually pretty much all there is to it. So I'm excited that it worked. Like it just worked. Awesome, right? Sorry. So yeah, and like just to show you, we could be like, we could change this and be like, so if you happen to be a React programmer, we could come here and run those commands again, which they're not going to be in my history here. So I'm going to steal them from here. So we will assemble it. And then we will, I don't know why, anyways. We will assemble it. We'll link it. Bam! Hello, React programmers! So yeah, I think that's pretty cool. We got our assembly working. I'm excited about that. So I did say I was going to actually talk a little bit about what stuff is like in software. So one of the things we talked about, if you're coming from like you did a boot camp or you taught yourself to program, to actually working on a team, a big difference will be communicating and coordinating on the team. And that seems obvious, right? But what does that actually look like? Like if all you've really done is your own programming and you're thinking about getting a job, what does it look like? So I can just tell you from my experience, my experience mostly covers like small, medium-sized companies. I did work at Zillow like 10 years ago or something, and they were a fairly larger company, publicly traded and everything, but nothing on the scale of like Google or Facebook or Cisco or IBM or something like that. So I really can't speak to those as much. But I've worked at a ton of different places, and there are definitely a lot of similarities. So like one of the big ones I was telling this person when I was talking to them about, things that are different from just programming for yourself, is using an issue tracker or a bug tracker. So this will be like, if we go to github.com. Okay, I'm not logged in, so GitHub issues. So if you use GitHub, they have a thing called issues. And essentially, they are a way of, it's like an issue tracker, a way of just tracking the progress on different parts of the project. And the first company I worked at, we didn't use any sort of bug or issue tracking until like a few years after I started there, but it's pretty universal at this point. You'll use something like this. And basically the general idea is things will get entered from two different paths. You'll have, oh wow, I'm not actually showing it. Anyways, so yeah, you have issues. You can create these issues. And essentially, one way you can use it as like an engineer, you're like going through the product and you realize you found a bug. So you can file a bug and you can write a description, you can write how to reproduce it. And this is just nice because it's kept track of. And if anyone else comes across this bug, they'll know it's already been found and maybe they can just add a comment with some more information about it. And then later on, you can assign that bug to somebody on the team to fix it. And so you can like set this XYZ person is working on it. And you can collaborate essentially that way. This is very basically universal. I would say nearly every serious software company uses some sort of issue or bug tracker. GitHub has their own. There's also another popular one is called Jira. It does things that are similar but can be way more complicated. There's a bunch of different ones, but the general idea is it's very useful when you're working on a team to coordinate things in like a written fashion. So if you're, just did a boot camp and you want to gain some experience that, might be more in line with the way things are done at a company, I would recommend just doing it on your own project. Like you can, you're working on your own project, you come across a bug you want to fix later, or even you have a feature. Like you're like, hey, it would be awesome if I had this feature for this. You can create an issue for it and write it down, and now you have it. And then later on, when you go to commit a fix or to add the feature, you can reference that issue. And so it's kind of all linked together and super useful because, when you're working in the real world, like it's a lot more messy, like you might get assigned to fix a bug in the bug tracker and you might think you fixed it and then it gets deployed and turns out somebody else ran into the bug, but it's slightly different than the way you fixed it. And so having a written record of how it was originally reproduced and showed up is super useful. You can be like, oh, I see, it's slightly different in this way, and you can go in and fix it. So yeah, the issue trackers are heavily used in software, programming. What it's like to be a software engineer. You'll spend a ton of time in an issue tracker in basically any place. And a lot of places will have like a project manager that will assign you tickets. The way a lot of places work is you'll go in on, Monday morning or whatever, and you'll have a view like, you see in this screen here, and project manager will be like, hey, I've assigned you these tickets. Or in some environments, you'll like sort of assign them as a group, sort of more agile way of thinking. And yeah, so if you're curious, you can check that out. I'm going to take a break before we get to the next one here and go look at our assembly code again, because, gotta give my brain a break here. All right. So what else do we want this actual program to do? If you have any ideas, let me know. Give me a second to get a drink. So my idea is, let's like, what if can we write out something dynamic, like adding two numbers together and like printing that out? Like, does that work? So without like doing research into how this works, we can look at our syscall here. So our syscall has this write, which takes a buffer and a size. Buffer is a pointer, I guess, to a memory location. Now, that makes me wonder, like, what if how would I print out? So let's say we wanted to do something like, we'll do it down here in a comment. So let's see, a comment syntax. So what if I wanted to do an assembly code 1 + 1, and I wanted to write that out to the screen, the result of it. So we'll say x = 1 + 1, and then I wanted to write out, so I wanted to do like write, 1 is just our file, no standard out file number, so not important. That's this line here. But then here, how would I write the value of x? Like, how do I do that? I can't just do it like that, which is what I want to do. And also, how would I know the length of it? Like, in this case, we could hard code it and be like, yeah, it's 1 byte. Does that work? Size t? I actually don't know. I'm just guessing. But maybe we want to do that, right? So I want to do something like that. So just for the sake of keeping our example here functioning, I don't like to just obliterate whatever it was I was working on. So we're going to copy it and paste it down here. And you can actually see that if we just assemble link and run it, it's just going to do it twice. So that's good. Our program still works. And just for the sake of showing you things, we could also do this. So you can come in here and we could make it message to length to change these things. And you could be like, sup world. And then we could come down here and change this, change those. And it should just work. Hey, awesome, cool. So that works. But now I want to figure out, like, can we do something else? So the way I approach things like this, especially if I'm trying to understand it and I don't know, I'm not reading the documentation, is what if we just simplify this and we know we want to print the character 2. So we can do this and it should just work. So let's try it here, and I'm gonna simplify this, and so I can run it all as one command. All right, so as you can see, it printed hello React programmers, a new line, and then just the number 2 and no new line. So that's to be expected. Now, can we hard code this length? So instead of doing len2, can I do number 1? Is that right? I don't know. Let's find out what happens. Assembler message error. Immediate value must be a multiple of 4. All right. What happens? So interesting. So we could compile it and run it, but it didn't seem to do what we wanted it to do. So my guess would be this value is the length of it is incorrect. And it's a question of what is the length of this? Is it 1 byte, 2 byte? So it's ASCII. So I would think it's 1 or 2 bytes. So it might be a byte is 8 bits. So we need to do that. I don't actually know. If you know, let me know. If that doesn't work, we'll just, keep doing multiples here. How about 32? Whoa, interesting. What did we do? What? Oh, look at this. Look at this. So we printed this out. Oh, fascinating. So look at this. Then we printed out 2. But what's all this? And I recognize this. So if you remember from earlier when we opened the object file, let's see if we can find the SH. Actually, if we open up the binary, we can probably find these labels in it. Yeah. So look, there's our 2. So we printed out all of this. Fascinating, isn't it? So let's wow, that's not what I wanted to do. All right, let's go back to hello.s. 32 is too much. 16 did not print out what we wanted. So this is not the recommended way of programming. I would recommend checking this out, but it can be also fun to like experiment. So that printed out a bunch of garbage. But if I remember right, 16 did not print out a bunch of garbage. So what about 18? Aha. Must be a multiple of 4, right? So that's interesting. So if we do the immediate value of 16, we get nothing. We do the immediate value of 20. Wow. So it prints out a whole bunch of stuff. I count equals length. So this is interesting. I don't really understand what it's doing, but maybe we can find out. So if we set it to length 2 like it was before, go back, do this, then we can open up hello. We read it from the disk. And all right, so we have our data. This will be a lot easier to read if I could do it in a hex editor. But in the meantime, I will do what I promised and talk about other things related to what it's like to work as a software engineer. So as a software engineer, what does it look like when you come into work on a normal day? So I think this is something, you'd want to know, right? And again, this would depend a lot on the company. But a lot of them will have like a daily stand-up. So it'll be like, theoretically, it's supposed to be a really quick call where everybody hops on, everybody on your engineering team, and you talk about like, hey, this is what I'm planning to work on today, or this is what I worked on yesterday, and these are the issues I could use help with or something. Just a way to kind of touch base. Some companies do it, some don't. Some do it on Slack or a messaging program. So this is also really common. Basically everywhere I've worked uses Slack or Microsoft Teams or something like that, and most communication happens over chat these days. When I first started, it was actually mostly email. So we'd have giant email threads, and you'd send out email like, hey, you want to go to Mission Burrito for lunch or whatever, and I would answer in an email. Then we got like text programs. So that's what most places use to do most of their communication these days. And a lot of engineers like that because it's a little bit more asynchronous and doesn't interrupt your flow if you're like in the middle of doing some programming. I'm going to look up how to trigger editing binary files in Emacs while I talk about this. So yeah, you'll come in to work and maybe sit down and probably you could start programming. It depends. Maybe you start your day when that meeting starts in the morning, when you have your touch base meeting, your stand up. But yeah, usually it'll be like that. And then a lot of times it's based around that ticketing system I talked about before. So when you're trying to figure out what to work on, you'll go look in that system and be like, hey, this is assigned to me as top priority or whatever. And you'll start working on it. So that's the standard way it works at most places. I would say most places I work at, they use chat primarily for communication, like I said. And the reason for that, I would say it's a bit frustrating because, I don't know, maybe this is just the normal work environment, but like as a programmer, we absolutely know it destroys your productivity to be interrupted by something. Like interruptions kill your productivity in a massive way. So like you're deep into some programming problem and your brain is like just in a completely different world trying to solve something or get something to work, right? And then somebody interrupts you. It could set you back hours. So programmers are naturally like not wanting to be interrupted. So it seems like what this has meant is that at a lot of companies, meetings are really frowned upon. So most communication takes place over email or text or something like that, because the idea is it doesn't interrupt you as much. And to some extent that's true, although I feel like at a lot of places it ends up being like there's kind of this expectation that you are replying to messages somewhat promptly. And I find that is kind of destroys my programming flow anyways. But again, this really varies depending on the company culture. Like I've been at some places where they make a really concerted effort to have blocks of time where you don't get interrupted, where it's perfectly fine to turn off your messaging program and just focus on programming. And they might put all of your meetings on one day of the week. That's kind of what I would say is pretty optimal because you're just not having to context switch all the time. But this varies dramatically. And I find most places there's like this pull towards having meetings because it's a lot more efficient to communicate, on Zoom or in person than it is over Slack and text messages. But if coordinating that and making that happen can also really interrupt your flow. And so I really like places that, are like, hey, Mondays and Fridays are meeting days. We try not to have any other meetings for engineers on other days. So you can work on programming on those days. You can know on Monday and Friday, maybe it's a time to like catch up on the issue tracker and make sure you've got it in sync with your actual work and communicate with your friends and whatever. Like most places though tends to be totally different where there's just constant pressure to reply on the text message app, whatever it is, but also be constantly programming. And that can be difficult, but that's just my experience. Curious to hear what you all think if you have a different one. Anyways, I remembered how to get Emacs to show us the binary of our program here. And I was hoping I could figure this out, but I am not sure that I can. So we can see this hello React programmers here. And we can see our number 2. And so you can, this like number 2 here, like let's say if we, so I think it's like this, these 2 bytes right here, maybe. You could like hard code this in place of this equals message 2, that'd be the memory location. But what we would really need to do, what I really wanted to do, is figure out what this equals len2 was. And if we go to so this is the text section. We need to go, or this is the data section, not the text section. Sounds a little confusing. Here is our .data section. And if you do enough assembly program, you'll start figuring out like, oh, 01 is the load instruction or the LDR instruction, and 40 is the, whatever. So you could start figuring this out, and you could be like, oh, okay, we're at LDR. You could find this line in our binary output and see what it's doing for the immediate value that it's, passing for the length. Because I don't know how to do that, I will have to, I think in this case, I'd have to look it up. Yeah, I don't have enough time on the stream to try to do it, but that is the way it works. So what we could do is something like ARM assembly, something like that. Immediate value, I don't know. I'm just sort of taking a stab in the dark here. Let's see, ARM32 mode, things are different there, and immediates can depend on the instruction. All right, so we might need to do ARM64 immediate value, immediate operand out of range. Oh, so maybe I can actually just do, maybe that's what I'm doing wrong. If we did, I don't know why that would matter, actually. Changing it to hexadecimal. Yeah. So it compiles. Immediate value must be a multiple of 4. So that works, but 16 does not. I'm a little bit confused. What if you did like must be a multiple of 4. I don't know. I'm taking a stab in the dark, and it's not proving useful. So this is the time when I would need to go back and understand what's going on. I don't think I'll be able to solve that on this stream, but I can talk a little bit more about, what it's like to be a software engineer. So I think another question would be, oh, hey, I had somebody send me a message. I don't know why OBS did not tell me that. But yes, this is assembly. So this is ARM64. We are, sorry, I'm not a great streamer, but yes. So I'm trying to get better. Anyways, yeah. So this is ARM64 assembly. I wanted to write a basic assembly program, and yeah, this one just prints out hello React programmers, and I was sort of messing around trying to figure out if I could get it to like print out a dynamic value instead of just a hard-coded value. But yeah, this is ARM64 assembler, and I am doing it because I built this operating system called the 3L project, which is made for x86-64 architecture, which is different assembly code, and I wanted to get some experience to understand, how it was different. So yes, that is the situation. But yeah, the last thing I wanted to cover about being a software engineer is like the so sort of the process that you would normally go through while you're writing code. So normally what will happen is you get these tickets, and it'll be like, hey, implement a feature that does XYZ, and you might get Figma designs or designs in some way that show you what it should look like. Maybe you will, maybe you won't. It depends on the place you work. But usually that's how it works, and you'll mark, hey, I've started working on this, and you go and you work on it, and maybe you have questions about how it should work, and you'll talk to whoever created the ticket or add them as comments on there. And eventually you get done writing your code, and maybe there's like other requirements, like it has to have tests with it or something like that. Once you've filled out those requirements, in a lot of places, what happens next depends. But a lot of times you'll create a pull request on like GitHub or something like that. And as a part of that process, it might run your code through the automated test suite and tell you if it passes. And then also once you do that, a lot of places have a code review process where somebody else on the team is required to read through the changes you've made and essentially evaluate them. And that process can be very, very, very extremely wildly like what that means. Some places are very strict about like style. It has to meet these styles, and they'll add comments like, hey, change this so it fits the style. Other places might focus on different aspects of it, but usually there's a code review process, and you'll get some feedback, and you might have to go back and make some changes, and then you push it to the pull request, and then eventually somebody else, or maybe two people or something on the team, approves the pull request. And once all the tests pass, it might get, you might be able to merge it in. So you'll merge it in, and it gets merged into, say, like the main trunk of the code base. That can also vary. That's how things get merged together and where it goes and what gets deployed and all of that. But generally that's the way it will work, is something like that. And then you can go work on something else. And, maybe if you have like a continuous deployment place, it'll just get deployed right then and there. But yeah, really depends on what the setup is. I like to have it so even when you create that initial pull request, it sets up an entire like environment so that people can go test it out and make sure it's working and does what it's supposed to do. You can go to your project manager, the QA team, and say, hey, can you make sure this does what it's supposed to do before it gets merged in and deployed? That varies a ton. So yeah, that's generally the way it works. And sometimes that gets deployed right away. Sometimes it's like a weekly thing. It just depends on where you are. And then it'll get deployed, and then you might get a bug report like, hey, it was supposed to do this, and now it does this or whatever. And generally the way it works is, once you've started working on an area of a code base or you have familiarity with it, a lot of places will continue to assign you bugs and features within that area. Not always the case, but that's generally how it works. So yeah, that's a little bit of day in the life of a programmer. And, let's just wrap this up. So I will say thank you all for watching and listening. And yeah, let's see if we can oh no, we still have to fix this bug here that I added. So this will be equals 1, 2. Thank you all for watching and listening. Bye. Although not bye yet, because thank you for joining me. And yeah, I hope it was interesting. If you want to see more stuff like this, or you have other ideas, let me know. Love to hear from you. Leave a comment, send me a message on thereactshow.com. Anyways, this was fun to take a break from React and that world and just dive into a different world that I don't know much about and just experiment with it. But yeah, thank you so much. And I hope you have a great one.